In this video, I would like to explain what's the thread of execution, how multithreading concept works, and why multithreading is important to understand. So let's get started, and the first question to answer is, what is a thread of execution? Imagine we have our CPU and a compiled program in computer memory. Once this program is compiled in its binary form, it becomes a list of instructions that the CPU can understand. For example, this Java example checks whether a number is prime. The if statement may generate a certain number of instructions. Each of these conditions will result in a number of instructions that have to be executed by the CPU, and every single statement will result in a number of instructions you can imagine would be required to run this code. So program execution means that the CPU is running these individual instructions. But how does the CPU know which of the instruction has to run next? Internally, the CPU has the instruction pointer, IP for short, which keeps track of the next instruction to execute. Instruction pointer is a CPU register, one of the variables built in directly in the CPU. Instruction pointer keeps track of the next binary instruction to execute. And as we keep executing these instructions, the instruction pointer advances forward and always has the memory address of the next available instruction in memory. This is the execution by the CPU. So then, what is the thread of execution? Thread of execution corresponds to a data structure maintained by the operating system. It has a copy of the instruction pointer in computer memory while the program is running. So operating system preserves instruction pointer of every program while it is running. And because instruction pointer is preserved in operating system memory, the execution can be suspended by the operating system temporarily, and later it can resume again at the same address. Every process in the system has at least one thread of execution, and we call it the main thread, which enters the main method in the main class of the Java application, or a main function in a C or C++ program. A program may request the operating system to create another thread and start executing two threads at the same time in parallel. Once we have this concept of a thread supported by the operating system, it becomes easy to create multiple threads and run multiple programs because it is simply a data structure in operating system memory that keeps a copy of the instruction pointer. However, we have only one CPU, but many programs and many threads of execution. So the next question is, how does the CPU switch between multiple threads? Okay, besides the CPU and memory, we also have other hardware devices connected to the system bus. For example, a mouse, a keyboard, touchscreen, and so on. So what happens when the user clicks a mouse or presses a key on a keyboard? In response to hardware events, the CPU suspends the current execution and switches to run the program to service hardware interrupt. So what is hardware interrupt? A hardware interrupt is a signal to the CPU that one of the devices needs attention. There is a table of hardware interrupt services, and the CPU gives that program a chance to process the request by the hardware. This happens very quick. The key is pressed on the keyboard, and it is preserved somewhere in operating system memory. The interrupt call returns, and the CPU continues to execute the program which it has been executing before. The program has no idea it was interrupted. It thinks that it has never been interrupted, like it's just running very smoothly and completely uninterrupted, but it's not true. It gets interrupted many times because so much more is happening in the computer system. So let's go back to the question, how does the CPU switch between multiple threads? In addition to the mouse and keyboard, we also have a system clock generator. It's another device we have in the system which simply makes its own hardware interrupt, which invokes operating system component known as thread scheduler. So the thread scheduler is invoked every time when the clock generator signals the system. So the thread scheduler makes its own calculation and looks up which of the threads should run next. Okay, so it has the sequence of threads that it thinks should be scheduled next, and the CPU switches to run that thread after each clock cycle. So the next program has a chance to run until the next clock cycle, which lets another thread of execution to run, and so on, and so on, and so on. A modern CPU is a multi-core, meaning that internally it has multiple instruction pointers that can truly run in parallel. Right, so we have those multiple core that can truly execute these programs in parallel. And some of these threads can be worker threads that run background tasks, do some computation, connect and load data from files and from databases, make network connections, transfer data over the networks. And other threads are dedicated to handle interaction with the user. On the server side, multithreading allows multiple server applications to run simultaneously. A server connects with multiple clients and assigns each client request to be handled by a separate thread. On a single user computer, like a desktop or mobile phone, multiple apps can execute at the same time. Additionally, each application is more responsive and easy to use because programs have separate threads that interact with the user and other threads that run in the background. So multithreading dramatically enhances application performance, the user experience, and improves the quality of the user interface.